My name is Dennis Davis. I'm an engineer, not a mathematician. I try to make my videos visually enlightening and fast-paced. But this video is very long because it covers almost the entire first year of calculus using visuals, graphs, and diagrams. I'd rather show you calculus visually than just tell you the rules and formulas. If you see where the rules and formulas come from, that can help you understand, remember, and make use of them. To become truly proficient at calculus, you'll need practice, which you won't get just by watching this video. In the description, I'll link to some helpful practice-oriented videos by others. Whether you're new to calculus, studying it now, or just want a refresher, I hope you'll find this video informative and engaging. My only assumptions are that you're already familiar with functions and algebra. So here we go. Calculus is the study of change and rates of change of mathematical functions. When we use calculus, we perform operations on functions that result in different functions. This isn't a new idea at all. We perform operations, such as addition, on numbers to get new numbers. We operate on sets to get new sets, on matrices to get new matrices, and we can operate on functions to get new functions. In fact, you've probably already done this in algebra when you had a function and found its inverse. We start with a function, f of x, and write out f in terms of x and y, so that y equals some function of x. Then we rewrite the equation switching x and y. Then solve the second equation for y, and that's the inverse of the first function. So we start with a function, perform an operation on it, and get a new function. The point is, taking an existing function and performing some operation on it to get a new function isn't a new or advanced math concept, and that's really what calculus is. In fact, calculus is all about performing two operations on functions. That's it. That's calculus. The first operation is called differentiation. When we differentiate a function, the new resulting function is called the derivative of the first function. The derivative is the first topic we'll cover. Learning to take the derivative of a wide variety of function types is roughly the first semester of calculus. The second calculus operation is called integration. When we integrate a function, the new resulting function is called the integral of the first function. Integration is roughly the second semester of calculus. And there's a wonderful relationship between these two operations that we'll get to at just the right time. When functions are simple, these operations are simple, and calculus is simple. It's when the functions we operate on get complex that calculus seems complex. So if calculus has a reputation for being a difficult subject, it's not really calculus's fault. We'll start with the derivative and consider a simple function. F of x equals x minus 1. This is a linear function, so its graph is a straight line. I said calculus was the study of change and rates of change, and the rate of change of a straight line is its slope, rise over run, delta y over delta x. I like to color code things in my videos. I'm using blue for x coordinates and distances, and yellow for y. And I'll use pink for slope or rates of change. I won't draw a lot of attention to the colors and may not mention them again, but their consistent use may let you see some apparent order or pattern that might not otherwise be clear. For a straight line, it's easy to find the slope. Just pick any 2 points and subtract their y and x coordinates to get delta y over delta x. Delta y is 3 minus 0, this distance, the difference between the yellow y coordinates. And delta x is 4 minus 1, this distance, the difference between the blue x coordinates. So for this linear function, the slope is 3 over 3, or positive 1. For every unit x changes, y changes by 1 times that amount, since the slope is 1. If the slope were positive 1/2, then when x changes by some amount, y changes by positive 1/2 as much. If the slope were negative 2, then when x changes, y changes by negative 2 times as much. That is 2 times as much, but in the opposite direction. Y would get smaller as x gets larger. When the graph line is horizontal, the slope is 0 because y never changes, so delta y is 0. When the graph line is vertical, the slope is undefined because x never changes. Delta x is 0, so delta y over delta x is undefined since the denominator is 0. Everything is nice and simple when the function is linear, but what about the function f of x equals x squared minus 2x plus 1? The graph of this function is a parabola, so now the question, what's the slope, prompts a new question in response. Where do you mean? Because the slope is smoothly changing, it's different at different points. Suppose we wanted to find the slope of the function at x equals 1.6 here. Now, if you know calculus, or more specifically the rules of differentiation that we'll cover soon, then within a few seconds you can figure out that the slope at x equals 1.6 is 1.2. If you don't know calculus yet, I promise that soon you'll know how to do this. But without calculus, it's not easy. After all, slope is right over run, delta y over delta x. But with just 1 point, where does delta y come from? Or delta x? Slope is the rate of change, and there's no change at a single point. There's only a change in changes. So it's a tricky question. By drawing our best attempt at a line tangent to the curve at x equals 1.6, then measure the slope. It won't be very accurate. It's not always easy to draw an accurate tangent line, but without calculus, that might be an option. But let me show another way. In the 1600s, the great minds that developed calculus approached the problem this way. I'll zoom in on our grid at the breadpoint of interest where x equals 1.6. We want to know the slope at the red point. I warned you I like to color code things. Let's choose a nearby point, green, and find the slope, delta y over delta x, between red and green. So we estimate the slope at red as the slope of the pink line between red and green, delta y over delta x. It'll be pretty close, and the closer green is to red, the better the estimate. This is the approach that will lead us to the derivative. The x value of our red point, where we want to know the slope, is 1.6. We find the y value by plugging 1.6 into the function, and we get 0.36. Let's choose a nearby x value for the green point. Let's say 1.601. So we find the y value for the nearby green point by plugging 1.601 into our function to get 0.361201. Remember, here's our function. Y equals x squared minus 2x plus 1. We can easily find the slope delta y over delta x between 2 points given their coordinates. And we get 1.201, the slope between red and green, which is our estimate for the slope at red. Calculus will tell us, I promise, that the slope at red is 1.2, so our estimate is very close. The closer we let green get to red, the closer the estimate will get to 1.2. So let's prove it. We'll still choose a nearby green point, but now, instead of choosing an actual small distance away from red, such as 0.001 or 0.0001, we'll use a variable for the tiny x distance to green and call it h. The coordinates of the red point are still 1.6, 0.36, but let's consider the coordinates of the green point. Its x-coordinate is 1.6 plus h, and its y-coordinate is the function's value when we plug in 1.6 plus h for x. Now let's find the slope as delta y over delta x. Delta y is the y-coordinate of the green point, f of 1.6 plus h, minus the y-coordinate of the red point, which is still 0.36. I'm shading the components to the color of the corresponding point, and delta x is the x-coordinate at green, 1.6 plus h, minus the x-coordinate at red, 1.6. The denominator, delta x, looks pretty easy to simplify. 1.6 plus h minus